a type of microwave devices. A tunnel diode is heavily doped PN junction diode. In tunnel diode, electric current is caused by tunneling. The tunnel diode shows negative resistance. The symbol of tunnel diode is shown here. Here is anode, here is cathode. In tunnel diode, the p-type semiconductor acts as an anode and n-type semiconductor acts as a cathode. A tunnel diode is also known as Esaki diode. The tunnel diode was invented in 1958 by Leo Esaki. Leo Esaki observed that if a semiconductor diode is heavily doped with impurities, it will exhibit negative resistance. Negative resistance means the current across the tunnel diode decreases when voltage increases. In 1973, Leo Esaki received the Nobel Prize in Physics for discovering the electron tunneling effect used in these diodes. The operation of tunnel diode depends on the quantum mechanics principle known as tunneling. In electronics, tunneling means a direct flow of electrons across the small depletion region from n-side conduction band into the p-side valence band. As tunnel diode is heavily doped PN junction diode, doping density of tunnel diode is about 1000 times greater than ordinary junction diode. So there is some effects of heavy doping. The width of depletion layer reduces extremely, produces negative resistance action in characteristics graph of diode, reduces the reverse breakdown voltage to a small value approaches to zero. Small forbidden gaps in tunnel diode allows conduction for all reverse voltages. What is tunneling? Tunneling is known as a direct flow of electrons across the small depletion region from n-side conduction band into the p-side valence band, shown by this arrow. In a p-n junction diode, both positive and negative ions from the depletion region. Due to these ions, inbuilt electric potential or electric field is present in the depletion region. This electric field gives an electric force to the opposite direction of externally applied voltage. As the width of the depletion layer reduces, charge carriers can easily cross the junction. Charge carriers do not need any form of kinetic energy to move across the junction. Instead, carrier punch through junction. This effect is called tunneling, and hence the diode is known as tunnel diode. This is the diagram of forward bias tunnel diode. Here is positive terminal of supply and here we connect negative terminal of supply. This side is p-type semiconductor, this type is n-type semiconductor. The depletion region is shown here. The depletion region is a region in a p-n junction diode where mobile charge carriers are absent. Depletion region acts like a barrier that opposes the flow of electrons from the n-type semiconductor and holes from the p-type semiconductor. The width of a depletion region depends on the number of impurities added. Impurities are the atoms introduced into the p-type and n-type semiconductor to increase electrical conductivity. In tunnel diode, the p-type and n-type semiconductor is heavily doped, which means a large number of impurities are introduced into the p-type and n-type semiconductor. This heavy doping process produces an extremely narrow depletion region. So applying a small voltage is enough to produce electric current in tunnel diode. The difference in energy levels is very high in tunnel diode. Because of this high difference in energy levels, the conduction band of the n-type material overlaps with the valence band of the p-type material. Quantum mechanics says that the electrons will directly penetrate through the depletion layer or barrier if the depletion width is very small. The depletion layer of tunnel diode is very small. It is in nanometer. So the electrons can directly tunnel across the small depletion region from n-side conduction band into the p-side valence band. So in general, in a conventional diode, forward conduction occurs only if the forward bias is sufficient to give charge carriers the energy necessary to overcome the potential barrier. When the tunnel diode is slightly forward biased, many carriers are able to tunnel through narrow depletion region without acquiring that energy. The carriers are able to tunnel or easily pass because the voltage barrier is reduced due to high doping. This is about working of tunnel diode. Now we discuss its characteristics. In first step, we see unbiased tunnel diode diagram. When no voltage is applied to the tunnel diode, it is said to be an unbiased tunnel diode. In tunnel diode, the conduction band of the N-type material overlaps with the valence band of the P-type material because of heavy doping. So when the temperature increases, some electrons, because of this overlapping, the conduction band electrons at N side and valence band holes at P side are nearly at the same energy level. So the net current flow is 0. Step 2. Small voltage applied to the tunnel diode. When a small voltage is applied to the tunnel diode, which is less than the built-in voltage of the depletion layer, no forward current flows through the junction. However, a small number of electrons in the conduction band of the N region will tunnel to the empty states of the valence band in P region. This will create a small forward bias tunnel current. Thus, tunnel current starts flowing with a small application of voltage. The third step is applied voltage is slightly increased. When the voltage applied to the tunnel diode is increased slightly, a large number of free electrons at N side and holes at P side are generated. Because of the increase in voltage, the overlapping of conduction band and valence band is increased. So the energy level of an N-side conduction band becomes exactly equal to the energy level of a P-side valence band. As a result, maximum tunnel current flows. Now, in step 4, applied voltage is further increased. If the applied voltage is further increased, a slight misalign of the conduction band and valence band takes place. Since the conduction band of the P-type material and the valence band of the P-type material still overlaps. Since the conduction band of the N-type material and the valence band of the P-type material still overlap, the electrons tunnel from the conduction band of N region to the valence band of P region and cause a small current flow. Thus, the tunnel current starts decreasing. So, here in this diagram, we see the tunnel current decreases. In step 5, applied voltage is increased largely. Since the conduction band of the N-type material and the valence band of the P-type material are no longer overlap and the tunnel diode operates in the same manner as a normal PN junction diode. In this case, when the applied voltage is largely increased, the tunneling current drops to minimum. If this applied voltage is greater than the built-in potential of the depletion layer, the regular forward current starts flowing through the tunnel diode. Now we discuss about its VI characteristics. As forward bias is applied, significant current I is produced after continuous increase of voltage. V current achieves its minimum value called as valley current. After further increase in V, current starts increasing as ordinary diode. IV is valley current, VP is peak voltage, IP is peak current, VV is the valley voltage, and IV is the valley current, and this is peak forward voltage. Now, if we summarize the working of tunnel diode, we can say in forward bias operation. At first, voltage begin to increase. Electrons tunnel through PN junction. Electron and holes states become aligned. When voltage increases further, state become misaligned. So current drops. It shows negative resistance. V increases, I decreases. As voltage increases yet further, the diode behave as normal diode. The electron no longer tunnel through barrier. In its VI characteristic portion, this portion shows negative resistance region. The portion of the curve in which current decreases as the voltage increases is the negative resistance region of the tunnel diode. The negative resistance region is the most important and most widely used characteristic of the tunnel diode. A tunnel diode operating in the negative resistance region can be used as an amplifier or as an oscillator. Advantages of tunnel diode. They have long life, high speed operation, low noise, and low power consumption. Here shown the reverse bias characteristics of tunnel diode. When used in reverse direction, they are called as back diode. In this, the electrons in valence band of p side tunnel directly towards the empty states present in the conduction band of n side, thus creating large tunneling current which increases with application of reverse voltage. Here is the diagram of tunnel diode reverse IV, which is similar to Zener diode. Now we come on the applications of tunnel diode. It is used as an ultra high speed switch due to tunneling, which is essentially takes place at speed of light. It has switching time of nanoseconds or picoseconds. Used as logic memory storage device, used in satellite communication equipment, used in relaxation oscillator circuits due to its negative resistance feature. They are used in FM receivers due to low power requirement. Tunnel diodes are resistant to the effects of magnetic field, high temperature and radioactivity. That is why these can be used in modern military equipments, NMR machines. Thank you.